Good afternoon. My name is Heidi Marais, and I'm a PhD student at Mäladalen University. Today, I will be presenting some of my work on the use of statistical process control charts for univariate sensor fault detection in wastewater treatment. One of the main reasons that we are interested in this topic is due to the importance of process supervision in wastewater treatment. This is made evident particularly when considering the restrictions that are placed on effluent quality. Fault detection is an integral component of process supervision for numerous reasons. Perhaps one of the most obvious reasons is the reliance that process control has on reliable measurements. The main goal of this work was to take simple univariate fault detection strategies and determine which performs best overall, taking into account several fault sizes and shapes to hopefully obtain an answer that is independent of the properties of the fault. The reason for using these basic methods was to obtain a benchmark to compare the performance of other fault detection methods to. It's very easy to overcomplicate a problem, and complexity does not necessarily equate to better performance, but also due to the potential that these methods have to be combined with more advanced methods. The specific methods that were used are the Shewhart, cumulative sum, and exponentially weighted moving average charts. These methods have been used for the wastewater treatment process in several previous works, but without a rigorous comparison allowing us to conclude on a single method that should be pursued further. We used the MATLAB Simulink implementation of the benchmark simulation model number 1 and introduced sensor faults to the nitrate sensor in the second tank. This sensor is used in the nitrate control loop, where the internal recycle flow rate is the manipulated variable. Part of the motivation of this was to have both a manipulated and a controlled variable available for monitoring. Both bias and drift fault shapes were used, with several fault sizes, and the figure shows example profiles for these two types of faults. The fault lengths were also varied throughout the simulations. The parameters of the chart-based methods, such as limit sizes and smoothing factors, were optimized offline without active process control. This was in order to find a trade-off between minimizing the number of false alarms, the time taken to detect a fault, and the number of misdetections. These three criteria were also used to compare the performance of the different methods. There were three main results when considering monitoring the nitrate sensor. Firstly, as the fault size increased, it was easier to detect the faults. Except for with the bias faults, where the cumulative sum and exponentially weighted moving average methods could detect all the faults, and with the drift faults, where the exponentially weighted moving average method had a constant detection time. Secondly, the methods performed in the listed order, considering the three comparison criteria. If one had a higher priority, there may be exceptions to this ordering. Finally, all the methods performed significantly worse for the drift faults than the bias faults, which leads us into the next result, monitoring the internal recycle flow rate. This is what you see at the top of the figure. In the middle, we see the nitrate sensor measurement, and in the bottom, we see the actual nitrate concentration in the tank. What happened in the simulations producing these results was a slow drift fault in the nitrate sensor, which the controller compensated for, resulting in a decrease in the actual concentration. We can see that the internal recycle flow rate changed from the normal pattern at this time, but because of the cyclic behavior of the flow rate, it is not well suited to be used with these chart-type methods. Despite that, though, we did consider how the results would change by monitoring this flow rate, and found that there were significantly more false alarms, but shorter detection times and lower misdetection rates for the drift faults that are so easily obscured by the controller. One last thing that may seem obvious, but is rarely explicitly mentioned or quantified in studies relating to fault detection, is the effect that faults can have on the process. Here we consider the change in the pumping energy caused by the presence of a fault, for different size faults with different detection times. you can quite clearly see that the presence of the fault has a detrimental effect on the energy requirements of the system. This is important to quantify and highlight, as it can be the key to getting these technologies into industry if we can clearly quantify the monetary benefits that they can provide. In conclusion, we saw that the exponentially weighted moving average chart outperformed the other methods for the fault shapes, sizes, and criteria considered. We also saw that the controller has a large effect on the ability to detect the faults, and we highlighted the effect that faults can have on the process and the subsequent need for effective fault detection. Before I conclude this presentation, I would just like to thank the project funders. This work was done within the Control for Reuse project, which is a water JPI project. Thank you for your attention and for your time. If you have any questions, you're welcome to ask them, or you can get in touch with me via email.